Yes, how do you say it? De moivres, de moivres. However, some French bloke came up with this idea. Okay, and actually, we've seen it before. So whether this idea was thought up first, and then we got the idea from it, or whether our other idea about if we raise a complex number to a power, we multiply the arguments by n. I'm not sure which way around it is, but that's basically what it's saying. We raise a complex number to the power of n, we multiply the argument by n. So we know that already, but it was formalised in this theorem. And in this particular theorem, it says for all integers n, reality is it actually works for anything. It doesn't have to be an integer. So we can, in fact, extend that to, if we chuck a modulus out the front as well, because we know that when we raise a complex number to the power of n, the modulus gets raised to the power of n. So if the modulus is not 1, we could write it like this. R cis theta to the power of n is r to the power of n cis n theta. So if we want to find 1 minus I to the power of 5, yes, we could expand the whole thing out. I mean, that would be a legitimate way of doing it. But what we do is we change it to mod arg form, the modulus of this one being the square root of 2. The arguments, now we've got to be careful which quadrant. We're down in the fourth quadrant, so it's negative acute, so it's minus pi on 4. So we're saying it's root 2 cis minus pi on 4 to the power of 5. So the root 2 gets raised to the power of 5, but the argument gets multiplied by 5. Root 2 to the power of 5 would be 4 root 2. Minus 5 pi on 4, well, that's not where we normally put it. We normally put the argument in between pi and minus pi. So if we were going backwards, minus 5 pi on 4, that's the same as going forwards, 3 pi on 4, isn't it? Yeah. So we could rewrite that as 4 root 2 cis 3 pi on 4. That would be the answer in mod arg form. Now, if they hadn't actually asked it in mod arg form and I had to work it out as a plus ib, then I wouldn't bother changing the angle because I'm going to go cos of the angle anyway and get rid of it. And it's going to give me the same answer, minus 5 pi on 4 or 3 pi on 4. So it depends how they want the answer. So if they did want it the other way around, I could now say, oh, well, that's 4 root 2 times the cos of 3 pi on 4 plus I sine 3 pi on 4. And cos of 3 pi on 4 is minus 1 on root 2. The sine is plus 1 on root 2. Multiplying that out by the 4 root 2, and there's our answer in a Cartesian form. So minus 4 plus 4i. So sometimes, certainly when we're talking about large powers, it's easier to put it in mod arg form, use de Moivre's theorem, and then convert back rather than expanding the whole thing out. Works nicely if we end up with exact values, like that one did. Otherwise, we don't end up with approximations, I guess, because we'd be approximating the number of radians. So this now gives us another way of finding square roots. But not only square roots, we could find any roots, because we know square root's the same as power of a half. Cube root, power of a third. So if I know z to the power of n is x plus iy, and z to the power of n is r cis theta, then if I want to find the nth root, it'll become the nth root of the modulus, but the angle would be divided by n. Because remember we're saying to the power of 1 on 2, or 1 on 3, or 1 on 4, whatever root we're saying. Well, that's the same as saying dividing by 2, dividing by 3, dividing by 4. But you'll notice also I've added in a 2 pi k, because when we're finding roots, there can be multiple answers. Square roots have 2 answers. So adding on the 2 pi k is just revolving around the circle. Because when we revolve around the circle one complete revolution, we're back in the same spot. And so that will create the next answer and the next answer. And we keep going round however many times we need to get the number of solutions. There is always the same number of roots as the, as the power we're finding. So cubed roots, there will always be 3 roots. Square roots, always 2. Fifth root's always 5, and so on. So z squared equals 4i. Well, so z squared is 4 cis pi on 2. It's a purely imaginary one, so I know its argument is on the y-axis, and in this case it's positive, so it'll be up at positive pi on 2. So the square root was basically what we're doing, because if z squared's that, we're basically finding the square root of 4 cis pi on 2. Well, square root of 4 is easy enough, that's 2. It'll be the cis, well, pi on 2 divided by 2, but again, we're adding in the revolutions to go around. In this case, I only need 2 solutions, so I'll sub in k equals 0 and 1. By the way, it doesn't really matter what number you substitute in as long as they're consecutive numbers. I could have, if I really wanted to, substituted in 27 and 28. It would work just as well, but they just would be stupid numbers to pick. Okay, so we end up with, well, if k is 0, we're saying pi on 2 over 2, which is pi on 4. If k is 1, we end up with 2 pi plus pi on 2, which is 5 pi on 2, divided by 2. We get 5 pi on 4. So there's our 2 square roots in mod arg form. If we were to calculate them out, cis of pi on 4 is 1 on root 2 plus 1 on root 2i, I should say. And the other one's minus 1 on root 2, minus 1 root 2 I, and we end up with root 2 plus root 2i minus root 2 minus root 2i. The interesting thing about solutions is you really only need to find one of them. Because if you imagine revolving around the Argand diagram, they're always evenly spaced. So as soon as I knew root 2 plus root 2i is a solution, the next one must be 180 degrees around. And so the direct negative of it would be the solution. If I was talking about cube roots, then I know every 120 degrees there's going to be a solution or so on. Because that's basically what you're doing with this 2 pi k divided by n. Because you're getting a revolution dividing it by the number of solutions. So you're adding on that many each time. Okay, another way. So here I could have done it diagrammatically. Ooh, there's a fancy word. I could have said, there's my first solution, 2 cis pi on 4. And because I know they're evenly spaced, the next one must be 180 degrees round, so a direct reflection through, and so that would be 2 cis minus 3 pi on 4. So once I know one, I can create all the others because I know about the symmetry of the solutions. Well, let's find the fourth roots of 16. So we know x to the power 4 is 16 cis 0. The fourth root of 16 is 2. That's right, isn't it? 2 by 2 by 2 by, yeah, is 2. That works out nicely. And so we'll have 2 pi k plus 0. So it's just 2 pi k on 4. I've gone 0, 1, 2, and 3 for my consecutive numbers for this one. And so I get 2 cis 0, 2 cis pi on 2, 2 cis pi, 2 cis 3 pi on 2. And so I have 2, 2i, minus 2, minus 2i. Another way I could think about it, if the coefficients are real, we said solutions will appear in conjugate pairs. Right? So, because this is real, as soon as I knew 2i was a solution, minus 2i had to be a solution. So for that reason, when they're real, sometimes people like to add in, instead of 1, add in plus or minus 1. Because that will get the conjugates. And so for this one, again, always start with 0. I'll sub in 0, then I'll go plus or minus 1, and I only need one solution then, and so I'd sub in 2, or it could be minus 2, doesn't matter which one, and that will get the fourth solution. Okay. If I did it with the diagram, there's my first solution at 2 cis 0, 4 solutions going around a circle, so I know every 90 degrees there'll be a solution. So the next one's over there at 2 cis pi on 2, then 2 cis pi, and then down there at 2 cis minus pi on 2. Woo. There we go.